All right, hi, and welcome back. So this video, we are going to be looking at solving some more logarithmic equations. Some of these are slightly more difficult than ones we've already looked at. So one of the things that we've talked about is when you look at a logarithmic equation, you want to decide what method are you going to use. And what I mean by that is we can use what we call the one-to-one, or we're going to convert. When we use the one-to-one method, we get our equations down to this. So 1 logarithm is equal to 1 logarithm, 1 to 1, and they have the same base. If that is true, you can set your arguments equal to each other. We use this method when you have logarithms on both sides of the equation. That is when we can use this method. Typically, when that is true, you're going to have a variable inside of both of the arguments. So that's the first method. The second method is just convert. So if you don't have a logarithm on both sides, you still want to get one side down, so log base b of x, and then it's going to be equal to some number. If that is true, then you just convert it into its exponential form. So that is our decision that we have to make from the very beginning. So what we do to make the decision is determine how many logarithms do we have and where are they. So when we look here, it actually looks like to start that I have logarithms on both sides of my equation. So my gut instinct is that I'm going to use the one-to-one method. But if I look at this logarithm in any detail, I see that it's saying log base 5 of 25. I know that log base 5 of 25 is equal to 2. So making that substitution, I get 3 minus 2, which is 1. Now, when I look at this, I see that I only have logarithms on one side of my equal sign. That means my end goal is to get this down to 1 logarithm so that I can then convert and solve. So we have to use our properties of exponents, our properties of logarithms to try and work it here. We know that in order to condense these, we first have to get rid of our coefficients. So I'm going to bring this 3 up, and that gives me log base 5 of x cubed minus log base 5 of 5x. Now that we've gotten rid of that coefficient, we can go ahead and condense. It's subtracting two logarithms same base, so that's the division rule. So we get log base 5 of x cubed over 5x equals 1. We are now ready to go ahead and to convert this into its exponential form. So I'm going to start with the base. Go find my exponent. What am I going to set it equal to? Always at this step, make sure that you evaluate whatever this is. And so 5 to the first is just 5. Now we're ready to actually solve for our variable. In order to do a solving like this, we know the first thing we always want to do is bring our denominator up. So 5 times 5x is 25. X equals x cubed. It is higher, a degree higher than 1, so I'm going to bring everything to the same side. We're now ready to factor this. I'm going to bring out that x first. Now I have x squared minus 25. Well, that's actually a difference of squares. So we get x plus 5, x minus 5. From each of these, I have a possible answer. I have x equals 0, x equals negative 5, x equals positive 5. So once again, I brought this up. I saw that this was larger than 1, so I brought everything to one side. We factored out the greatest common factor, we factored the quadratic, and we got our 3 possible answers. Now I said possible answers, write them over here. X equals 0, x equals positive 5, x equals negative 5. They're possible answers because when we're talking about logarithms, there's a domain issue here. The argument must be positive. That means the argument can't equal 0, nor can it equal a negative number. So we have to plug each of these back in to double check that. So let's start with 0. If I plug this in and make it 0, well, immediately, that's not a positive number, it's 0. So that one doesn't work. Let's try positive 5. That's a positive number, it works. 5 times 5 is a positive number. That one does work. Let's try our last one, -5. If I put in -5 here, that's a negative number, does not work. So our only answer here is going to be x equals 5. So once again, for this one, the very first thing I noticed was I could evaluate this logarithm. By doing that, I saw that it was logarithms on one side, so I condensed it down, converted it into exponential form, and then we used our algebraic properties to solve for x. Once you solve for x, you have to go back and check your domain. So let's try another one. We're going to start once again by determining how many logarithms we have on each side. And from the very beginning, I see I have a log base 4 is equal to log 4, log 4. Each of these have a variable in it, so I can't evaluate them. So I know that eventually I'm going to use the one-to-one method. This side is already 1, 2. Oh, this one has 2. So we have to combine these. Because it is addition, we know that we can go ahead and do the product rule. So that's going to give us log base 4 of 2x plus 1 equals log base 4 of x minus 3 times x plus 5. We know that in order to multiply these together, we're going to multiply each part by each part, each term by each term. So that gives me x squared plus 2x minus 15. Now I have one logarithm set equal to one logarithm. The bases are the same. So now we're ready to use that one-to-one property. We're just going to go ahead and set those arguments equal to each other. Once again, I see that this is a quadratic, so I know that I need to set it equal to 0, which means bring everything over to the same side. Once again, we have a difference of squares here, so this factors to, pardon there, x plus 4, x minus 4. So I have the possible answers of x equals -4 and x equals +4. Once again, we have to go back and double check. So we actually have to plug these numbers in. So let's start with the -1 because that's typically the one that gets us in trouble. Typically, but not always. So I'm going to do 2 times -4 plus 1. That gives me -8 plus 1. That's going to be a negative number. So immediately I know this one does not work. I also have to check the positive one because sometimes it won't work either. Well, 8 plus 1, that's 9. That's a positive number. 4 minus 3 equals 1. That's a positive number. 4 plus 5 is 9. That's a positive number. So we have our final answer. All right, I got 2 more for us. These ones have to do with natural logarithms and e, and it's just because I wanted you guys to see what it would look like when we throw these in. So here, if we look at it really quickly, we have logarithms set equal to logarithms. So we know we're going to want to use the one-to-one method. Right now, it's 2 to 1, or sorry, 2 to 2. So we need to get these down. So once again, here it's addition. So I'm going to multiply these. That's going to give me the natural log of x squared plus x. Here it's subtraction, so I'm going to divide these. So I get the ln of 4x over 2. I actually know that 4x over 2, 4 and 2 reduces to be 2x. So I'm going to go ahead and simplify that. Now I have one logarithm set equal to one logarithm. So we have x squared plus x equals 2x. Once again, this is a quadratic, so I'm going to bring everything over. So x squared, and subtract that 2x, minus 1x equals 0. So it's x minus 1, x equals 0, x equals 1. Just again, we always have to go back and double check. Do these work? So we're going to start here with 0. Well, that one doesn't work right off the bat. 1, that's a positive number. 1 plus 1, that's a positive number. 4 times 1, that's also a positive number. We are good to go here. So when we're solving, the fact that it's a natural log here didn't really do much. Had it been one where we had to convert, so let's just say, for the sake of it, I had the ln of 5x plus 2 equals 8. Then we would actually have to convert this, so the base would be e to the 8 equals 5x plus 2. Here, we would actually leave e to the 8 as e to the 8. So my final answer for this one would be e to the 8 minus 2, all divided by 5. So if we aren't doing an application and we can leave it as e to the 8, we actually leave it as e to the 8. This allows us to have the most precise answer. Also, if it is an application, you want to leave it as e to the 8 until the very end, and then you would put this in your calculator. Just to show you what this would look like if I did put this in my calculator. Really cool, your calculator has an e button. Most of the time, e to the power is the same thing as your ln button. You just have to get it to the alternate setting. So I'm going to do e to the 8th minus 2, all of that divided by 5. And here, for this problem I just made up, x would be approximately 595.79. But most of the time, people are going to expect you to leave your answer like this unless you are in the world of applications. All right, I got one last problem for you guys. Let's go look at it. So this one, very, very similar to this, but it starts in an exponential form. So here, the very first thing we need to do whenever you have an exponential is get it by itself. So I need to get rid of the 3. That gives me e to the 2x minus 1 equals 27. Now, there are different ways to go about solving this. Some of you guys will just want to convert it straight into logarithmic form. So it's base e. So I immediately know I'm going to do the ln of 27 to the 2x minus 1. So that is one method. Another method is to take the natural log of both sides. So since the base is e, I can actually just take the natural log of both sides. Our really cool property says that if the base and the argument are the same, this side simplifies down to the exponent. So I can cancel that out and I get 2x minus 1 equals the ln of 27. It just depends on what step you want to take there. Some people find this idea a little bit easier to do. They don't have to worry about the conversion. Some people just like to go to the conversion straight away. Either way, you get the same answer. Now we can go ahead and finish this. So we get the ln of 27 plus 1 equals 2x. So x equals the ln of 27 plus 1 over 2. Very similarly to this one, oftentimes you'll actually just leave your answer like this. We don't know what the ln of 27 is off the top of our head, so we can leave it like this. However, if you were something, once again, when you were asked to be an application or all equivalent expressions, you might want to actually try this one out. And you get the ln of 27 plus 1 divided by 2, and that's approximately 2.15. So you'll see when I approximate, I typically give just about 2 decimal points. But there you have it. Here's some other examples of solving logarithmic equations. This one is obviously an exponential, but we used a logarithm to get there in the end.